our first quiz of the new year. We have a quiz on day 4 of this week, or the last day of the week. And that quiz is on balancing equations, and then this new thing on reaction types. So Unit 4, as I mentioned, is a really short one. Last week we talked about the law of conservation of mass, and we started balancing equations. This week we're in 4.2, we're wrapping up balancing chemical equations, and the only other thing we need to do is figure out the types of reactions. And then we're just going to have a quiz for our assessment. And as I said, that quiz will be the last day of this week. Now, all around us, there are literally millions of reactions going on. Within our own body, there's millions of reactions happening every second. When you breathe in and breathe out, that transfer of oxygen is critical. And remember how small atoms are. So when you breathe in, you're breathing in tens of billions of oxygen atoms. And those oxygen atoms they're moving throughout your entire body in the capillaries to get to your tissues so you can move around. And basically, for that reason, because there's so many reactions going on, scientists want to try to classify them. And they can really classify them into 5 different types of reactions: synthesis, decomposition, single replacement, double replacement, and combustion reactions. So we're going to talk about them. I've given you this chart, but what I haven't given you is the type of reaction. So if you have 2 individual things that come together, another word for combination or creating things is synthesis. If you can synthesize something, you are creating it. So if you could take 2 elements and smush them together, that's called a synthesis reaction. So in your guided notes, get synthesis next to general equation. I'm never going to quiz you on the general equation, but you'll see it's helpful to have it written down. If you start with one reactant and that one reactant splits apart, that's called a decomposition reaction. If something decomposes, it breaks down. So if you start with one thing and then that one thing falls apart into a couple of other things, so there's multiple products, it's a decomposition reaction. Now, in a single replacement reaction, you'll start with one element that's symbol. Here, I'm just calling them all A, B, C, and D, but it could really be any single element. And then an ionic compound. So a single element in an ionic compound. And what's going to happen is the metals will switch places, in which case you'll end with a different single element. In a double replacement reaction, both of the metals will switch. So they will both replace each other. That's called a double replacement reaction, when both metals switch places. So if you look carefully, we start with A, it's stuck onto B. Whoops. C is stuck onto D. So my metals, A and C, just swap places. So now A is next to D and C is next to B. In a double replacement, both metals just replace each other. They just swap where they are. Combustion reactions are unique. Combustion reactions always start with a carbon-hydrogen bond. They react with oxygen, and they make CO2 and H2O. Combustion reactions are really what power our lives, not only our own bodies. That is the reaction that powers our own bodies. It's also the reaction that photosynthesis and cellular respiration, but it's also the reaction that gives us energy to heat our homes, our electricity. Combustion reactions are critical, and we'll talk more about them on the next slide. So this general equation here is just to kind of help you identify the reaction types. But I think there's maybe an easier way to do it, and that's what's next in your guided notes too. Okay, so how can you determine if you have a synthesis reaction? Well, if you have a synthesis reaction, you have 2 things that combined. Synthesis reactions are also called combination reactions because they combine together. So A plus B forms AB. 2 reactants make 1 product. I wrote down a quick example. If you start with lithium and oxygen, you have 2 reactants. If they come together, it'll form 1 product. Now, you would never need to predict the products. You would just need to be able to recognize, well, we're starting with 2 reactants and we're forming 1 product. So this is a synthesis reaction, which is the opposite of a decomposition reaction. In a decomposition reaction, you start with 1 reactant and it decomposes. It splits apart. 1 reactant makes 2 products. For example, if we started with cesium fluoride, this ionic compound right here, 1 reactant, just one thing to the left of the arrow. It's the only one where you'll have 1 reactant. That 1 reactant will split apart. So we have element cesium and element fluorine. If that splits up, it's a decomposition reaction. One reactant makes two products. Synthesis and decomposition reactions are opposite of each other. If you synthesize, they come together, and if you decompose, they fall apart. Next comes single replacement and double replacement. So think of synthesis and decomposition together, think of single replacement and double replacement together, and then combustion is completely on its own. Single replacement's over here. Hang on. No, I'm over here. In a single replacement reaction, one element is going to start single and a different element is going to end single. You'll always have one single element in the beginning and a different single element at the end. Okay, so in this example, element Ag, which is silver, starts single. It reacts with an ionic compound, and that's typically what we'll see, a metal and a nonmetal compound. It doesn't have to be that way, but most of the time it will be. And what we end up with is lithium as single. So what's happened here is this metal has come in and just kicked out this metal. So how are you going to be able to identify a single replacement reaction? One element starts single and a different element ends single. Finally, we have a double replacement reaction. In a double replacement reaction, the two metals will swap places. So we'll basically start with paired compounds. A metal and a nonmetal reacts with a metal and a nonmetal, and those metals switch places. So in this example, I start with the paired compound NaO, or Na2O, because sodium's +1 and oxygen is -2. That compound reacts with BeF2. So the double replacement are pretty easy to identify because you have paired compounds. In synthesis, you have individual elements coming together. In decomposition, you start with just one reactant. In single replacement, you have one thing that's single. In double replacement reactions, it's the only one where you have two ionic compounds, a metal and a nonmetal. And what's going to happen is this sodium will come in and switch with beryllium. So now sodium is going to be next to fluorine. And beryllium is going to switch, so it'll be where sodium was, beryllium will be next to oxygen, which is exactly what we see. Sodium has come in and kicked out beryllium, sodium is next to fluorine, and beryllium has moved over and it's next to oxygen. Okay, so I just cleaned up my notes a little bit. To remind you, synthesis and decomposition reactions are pretty easy to identify if you think about them, on their own. So in a synthesis reaction, you take two elements, and that general equation that I told you was element A reacts with element B to form compound AB. So what I'm trying to tell you here is that element lithium reacts with element oxygen to form lithium oxide. You won't have to predict products, but what you need to be able to recognize is two reactants make one product. And decomposition is the reverse. So compound AB or compound whatever splits up into the elements that make it up, A and B, which in this case are cesium and fluorine. Again, you don't have to know what forms, but just if you start with one reactant and it makes two products, then it's a decomposition reaction. In a single replacement reaction, you'll start with one thing that's alone, which I called element A. It reacts with an ionic compound, Bc. And what happens is that now a different element ends single. So something is going to switch and you'll have a different element ending single. One element starts single, one element ends single. And in a double replacement reaction, hang on, let me write out the general equation. You start with metal A bonded to a nonmetal, metal C bonded to a nonmetal, and the A and C switch spots. So sodium is now going to be where beryllium was, and beryllium is going to be where sodium was. So Be ends up next to O, and Na ends up next to F. Again, you just have to be able to identify these reaction types. Synthesis and decomposition are reverse of each other, and single and double replacement are very similar, but single replacement, something starts and ends single, or in double replacement, they stay paired the entire time. The last type of reaction is unique in and of itself, and it's a combustion reaction. In a combustion reaction, you'll always have some kind of carbon-hydrogen bond. One of the reactants has only carbon and hydrogen. It's always going to react with oxygen, O2, and it will always make CO2 and H2O. So the general equation that I gave you was CXHY plus O2 makes CO2 and H2O. So that reactant and these products are always the same. What can change is the X and Y here. So this could be like C2H4 or C3H6 or C4H12. It's a carbon-hydrogen bond. It's always going to react with oxygen, and it will always make CO2 and H2O. Combustion reactions are pretty easy to identify because they're the only ones that always make CO2 and H2O. And as I said, combustion reactions power you and our lives. So another really common product of combustion reactions is energy. And they do. They absolutely make energy. Now, I know this is where your guided notes stop, but I want to just do a couple more practice problems. So bear with me here. If you follow me, it'll make the assignment today a lot easier. It's annoyingly not letting me write on this document right here unless I start this over. So I'm just going to go with it. This is the worksheet from yesterday. Yeah, it's the one that had you balance the equations in part 1 and then check your answers using that simulation in part 2. But what if I told you that all of these reactions could be classified using the 5 types of reactions that we just talked about today? If we look at this first one, we start with a carbon with 4 hydrogens reacting with oxygen to form carbon dioxide and water vapor. What kind of reaction is that? I hope you can see it's a combustion reaction. It's a combustion reaction because we start with the CH bond, C1H4. It reacts with oxygen to form CO2 and H2O, and it always will form CO2 and H2O. It will always start with a carbon-hydrogen bond reacting with oxygen. This first one is called a combustion reaction. In the second one, we start with Na, a metal, stuck onto phosphorus and oxygen, nonmetals. That reacts with potassium stuck onto oxygen and hydrogen, nonmetals. What we have in this case is 2 paired compounds. And if we look carefully, this sodium, this metal, is going to swap with this potassium. Na comes in and replaces K. So now Na is next to OH. Na is next to OH, and K is next to the PO4 compound. So we have the 2 metals swapping places. What kind of reaction was that? That's a double replacement. We could call element Na A and PO4 B. Element K we call C, and OH we call D. Those 2 metals have just swapped places. So now C, which was K, is going to be next to what A was next to. So C is going to be next to PO4. K is going to be next to PO4. And that's exactly what we see right here. Okay. In example 3, we start with Mg, which is a metal, stuck onto F, and Li, which is a metal, stuck onto C. If we look carefully, this Mg will replace the Li. Mg ends up next to the C. That's what lithium was stuck to. And lithium is going to replace the Mg. So Li now is next to F, and Mg is next to CO3. What kind of reaction is this one? Yeah, it's a double replacement reaction. Are we seeing that it's a double replacement? The double replacement reactions, in my opinion, are the hardest to identify. But if you remember that it's 2 paired compounds and then the metals switch places, I think you'll do okay. All right, let's try example 4. In example 4, we had element P reacting with element O, forming just one product here. Do you see how there's just one product? If there's just one product, it's a dead giveaway that it's a synthesis reaction. Synthesis reactions are the only ones that have one product. Look at these other ones. On the right side of the arrow, on the product side, they all have multiple products. Synthesis is the only one that has one product, and decomposition is the only one that has one reactant. So example 4 right here is a synthesis reaction. In example 5, we have Rb next to nitrogen, and we have Be next to fluorine. Take a minute. See if you can figure out the type of reaction here. It's one we've done before. I would hope that you could see that rubidium swaps with beryllium. Rb and Be swap places. Be used to be next to F, but over here it's next to the NO3. Be comes in and replaces Rb, and Rb ends up next to F. These 2 metals have swapped places with each other. I did a couple extra double replacement reactions because, again, I think they're the hardest ones to identify. But you know you have a double replacement if you're starting with 2 paired compounds and those metals just swap places. Okay, finally, in this last one, we start with a paired compound. Ag is next to nitrogen and a single element copper. Okay, so what happens now is we end up with a different single element. So what kind of reaction is this? We start with one thing single, It swaps places, so now something else is single. This is called a single replacement reaction. So for the rest of the day, what are you going to try to do? Practice your balancing because that's on the quiz, and practice the identifying the types of reactions. If you have any questions, let me know. We'll do more practice with this again on day 3, and then we have a quiz on day 4. So if you have any questions, send me an email. Otherwise, I'll see you next time.